Welcome, Spidey Physics fans. Today I got a quantum mechanics problem. This is problem 1.4 from the Griffiths Introduction to Quantum Mechanics. We're going to solve this problem with no external help. I'm just going to spit out knowledge. I've taken this course before, so I kind of have an idea of where to go, but it's still going to be challenging. So I don't know how long this video is going to be. I might make mistakes. I don't even know the answer. We're going to check the answer somehow online. Maybe I'll find a solution manual. Maybe we're going to ask our boy ChatGPT. Do not trust AI for math homework. Maybe I will tell you guys how I use it, but don't rely on this stuff to help you out. So a few things I want to say before starting the video. Like I said, I don't know the solution, and my style of studying here is to slam a problem with no external help. If you don't know what to do, first thing you should do is look in the textbook and try to find something. I already kind of know what I have to look for, so I'll show you guys in the textbook what I'm using to solve this problem. But you always have to try to attack the problem by yourself. No solution manual. Try it out. It's okay if you don't know what to do. List out the things you know how to do, the things you don't know how to do. Attempt something, attempt it again, and then at the last resort, check a solution manual. Honestly, I would even recommend talking to a friend or talking to the professor or talking even to your parents or somebody about this problem before checking the solution manual. This goes for anything physics related, even chemistry, even math, whatever. Try it out by yourself. You're gonna thank me. So here's the problem. I'll pull out a laser pointer and read it out with you guys. At time t equals 0, a particle is represented by the wave function, and here they give you the wave function, and here they give you a series of functions. Here's function 1, here's function 2, here's function 3. We have a range for which this function is active. Where x is between 0 and a, this function is active. If x is between a and b, this function is active. Any other scenario, so if x is past b or if x is past 0, the wave function is 0. Where lowercase b are positive constants, we have a, b, c, d, e. Lots of problems. I don't know if we could solve all of them today. I'll let you guys know kind of a blueprint of what I think we're going to do. Normalize psi, the wave function. That is, find a in terms of a and b. I think we can do that. I have an idea. I'm going to tell you guys how we can do that, and we're going to try it out together. Part B is sketch psi of x at t equals 0 as a function of x. So we literally have psi of x over here. We have x over here. Sketch what the function looks like. We have part C. Where is the particle most likely to be found? This is where things get a little bit tricky because, as you saw in my 1-hour read-through, there are many different things that can answer this question. Maybe I shouldn't say that. Maybe there's one thing that can answer this question. But there are many different ways of thinking about where the particle is most likely to be found. So anyway, where's the particle most likely to be found at t equals 0? What is the probability of finding the particle to the left of A? So to the left of A. Check your result in the limiting case. B is equal to A and B is equal to 2A. I don't know what this limiting case means. We're going to get to that. Don't stress about it. And here is why I think this problem is going to be confusing. What is the expectation value of x? So we have expectation value of x, and where is the particle more likely to be found? Okay. Is that the same thing? Who knows? Most likely it's not. Maybe it is, though. Maybe it is the same thing. We're going to figure it out. So first things first. Before we get into anything related to the theory, I'm going to write down what we know. So this is probably like sketching psi, but we have the function psi of x at t equals 0. So this is like essentially just a single variable function of x. This equals a, and then how this is written is x over a. Right? These little brackets here, I'm just writing it like this. In fact, we can even write it as this, a over a x, because these are constants. So this is a straight line with slope a over a. Awesome. What does this look like? This is literally just a straight line like this. And this slope over here is this slope over here. Maybe I should pull out this little color here. So this is the slope of the function. Nice. Now this is for the region, let me draw this in blue actually, 0 less than equal x less than equal lowercase a. Whoops. So at some point here, we reach a, and over here is 0. So this is what the function will look like in this region over here. Is that cool with you guys? Now let's pick another color. Let's go with this little salmon. And let's do psi of x is equal to, let's do this part right here. A b minus x, so I'm going to do everything at the top, b minus x, and at the bottom there's another set of brackets, because there's this division symbol right here, b minus a. b minus a. Let's rewrite this in a more suggestive way. I think we could do a, b minus a, all of that being multiplied by b minus x, right? And we can take this entire thing right here and we can distribute it boom here, and we can distribute it boom right there. So what this is going to look like, let's actually draw that right here. We have a, b, and when we FOIL over the second time, we just have the thing in the front. So we have a, b minus a, x. So why am I writing it like this? Well, we have negative a b minus a x plus a b b minus a. So this is again a straight line. Here is x. Here is a negative sign and this constant right here, and this is all constants, right? Because the problem tells us it's constants right here. So we know that this line goes downwards, and over here is another constant. This is actually the y-intercept. So this function very like generally it looks kind of like this. And then over here, this green is this thing right here. And the slope of this is negative, it's going downwards, and the value of the slope is this parameter here. It doesn't really matter. All I'm trying to show you guys is that this first function right here, including this, is just a straight line going up, and this second function is just a straight line going down. Everywhere else, this thing is 0. So you don't have to do all this. Maybe you can look at it and kind of think about this more generally. But now let's actually draw the full thing of psi. Boom, we got x over here. Let's draw some cool pink right here. So this is where x is equal to a, and then maybe right here, we'll do here x is equal to b. I'm assuming a is less than b because of this thing right here. A is, so first there's 0, then you hit a, then you hit b. So here x is equal to 0. So basically what we saw, I'm going to draw a sign, this green. We increase, we hit some maximum value here, we decrease, we hit this, and for everywhere outside these bounds, the wave function is 0, right? So this is the wave function. I'm going to draw this little zigzag line to make it more apparent. This is the wave function. It's literally a triangle. Now, where exactly is this point over here? We're not sure. I actually think it should be a, because let's take a look at this function. If I plug in, so maybe I can do this a bit more clean. Right here we have the function psi of x is equal to, I think it was a over a times x, right? A over a times x. Cool. Now let's plug in a into x. So what we're looking at is psi of a. This is equal to a over a times a. These a's cancel. So exactly at a, the value of psi is capital A. Okay? So we know that this point here is at a y value of a. All right, so now we know absolutely everything we need to know about the function. By the way, I drew this slope and this slope to look almost exactly the same, but they actually shouldn't be the same. So maybe the function goes like this and then kind of like that. So this slope is different than this slope, but it really doesn't matter. The slope of the second function is over here. That is this slope. And the slope of the first function is here. That is this. But since we don't know the values, it doesn't really matter. So don't stress about it. I'm just drawing this picture so you guys can visually see what's going on. So this effectively almost answers this guy. Sketch this as a function of x. We pretty much know everything. We know where the function starts, where the maximum point is, what the maximum point is, where the function ends. Technically the function continues here, but here it equals 0. And we also know the slope of each of these as in terms of b and a. The only thing that we have to do is find a in terms of a and b. So once we do this, we can actually say what this is, and then we'll have all the information to answer a and b. Does that make sense? So now we have answered b, basically. We're going to go boom, and then now we have to answer this, normalize psi. If you guys hit the book and you go to the normalization section, you will see this equation, which is boxed, and this is the equation that we're going to use. So I'm going to write this equation down over here. How do you know to use this equation? You basically got to do a bunch of problems. But you could also read a bit of the theory, and you should kind of see how this equation is used. So basically what this equation is telling us is we have xt here, absolute value squared of the wave function, dx specifically, is that true? Boom. And now we have 1 over here. So this equation is going to help you get the normalization constant. Check it out. On one side of the equality, we have number 1, which is known. On the other side, we have some operations that we have to do. So we have to integrate over these bounds right here. And inside the integral, the integrand, we have to put our wave function, which we just found. We know every value of the wave function. The wave function looks like this. And then we manipulate some stuff. Over here, there's going to be an a and some numbers. We move stuff all the way to the other side, and we get a is equal to some number. That's how we're going to do this, guys. That's how we're going to do it in every single problem that asks you to find the normalization constant a. You're going to use this equation a lot, so this is going to be an important problem. Awesome. Now, this thing, right, is our wave function. And if you think about what an integral actually is, it's basically asking you, what is the area under this function? Okay, and it looks like we only have this area here. Everywhere over here and everywhere over here, there is no area because the wave function is 0. So we can break up our integral into 3 sections, or several sections. In this section here and in this section here, the area is 0. So basically we just have to do an integral over here and an integral over here. If you want, you could literally just go boom, boom, boom. This is a triangle. You do base times height, multiply those guys, divide that by 2, and there's your area. Honestly, I think I'm literally going to do this. And then we're going to do the integral to see if it matches up. So capital A, lowercase a divided by 2, that is the area over here. Boom, boom, boom. This is the second triangle. This is from A to B. So what is the base over here? The base is B minus A. This is the value of the base, right? Because you go scoop, and then you take this, you subtract these two, and you just get this value here, right? So we have B minus A as the base. The height is still A. You multiply this, you divide both of those by 2, and that's the area of this triangle. Obviously, if the wave function was some other crazy thing like this, we would have to use an integral. But since it's a simple shape, you could just use some elementary geometry, figure it out. So, boom, the integral from -infinity to 0 of the wave function, absolute value of the wave function, dx, plus the integral from 0 to a of the wave function dx, plus a to b, absolute value of the wave function squared dx, plus the integral from b to positive infinity, absolute value of the wave function squared dx. All of these together is exactly what I told you guys. Here's region 1. That is this region here. Here's region 2. It starts from 0 and goes to A. It starts from 0, it goes to A. So this is region 2. Okay. Over here we have region 3. It starts from A and goes to B. It starts from A and goes to B. That is region 3. And region 4 goes from B all the way to infinity. From B all the way to infinity. And this is 0. So pictorially, this is what it looks. In calculus, this is what it looks. So this entire integral literally equals all of this. You can write this integral here, then you could do an equal sign, followed up by all these integrals here, and this is valid. So this is how I normally solve the problems. And from here, I do this. This equals 0. This equals 0. And what we just found was that this region over here equals, what was it? A times A over 2. Base times height over 2. Nice. Now we have this region over here. I'm sorry if you guys can hear some sounds in the background. Please try to focus with me. So this one was base, which is B minus A, times height over 2. So all we have to do is add those up. Let's go back to this original color. We have AA over 2 plus B minus A times A over 2. This equals 1. Why does this equal 1? Because effectively what we just did was calculate this integral, so I'm just doing this equals 1 over here. This is the value of the integral, equals 1 over here. Okay, I'm just going to box this very quickly because what I did was elementary geometry. I kind of want to do an integral because, I don't know, it's good to double check math, right? So this part here, let's call this section 1. The integral here was from 0 to a. The wave function was a over a times x dx. Where am I getting this from? Well, that is the exact value of the wave function. Remember, we found it right here. So just go check what this part of the function actually was and plug that into here. And the only thing we have to do actually is boom, boom, squared, right? Because we have absolute value of the wave function squared. What does absolute value mean? It just means take whatever is negative, make it positive. But in this case, the square does that. So we're going to expand this integral. Here we have the integral from 0 to a. Then we can apply the square everywhere. So a squared, lowercase a squared, x squared. Then we have dx. A and a are constants because our problem told us they were constants. So we can pull them out of the integral. We have a squared. Oh, guys. See, this is what I'm talking about, bro. This is actually wrong because we're not finding the area of psi. We're finding the area under psi squared. You see why checking is good? So this is actually incorrect. You know what? We're still just going to leave it here, but I'm going to put a star here. Let's do not correct. All right, so that is one big mistake I made. Thank you guys for joining the video. Let's keep working. We have a squared, a squared. Then we can have our integral. Boom. Here we have x squared, and then we have dx. So now with the constant outside stays the same, it is a squared over lowercase a squared. The integral of this has to be a cubed over 3 because the derivative brings the 3 down. The 3 cancels with the denominator, and you do 3 minus 1, which equals 2, which gives us x squared. If you guys don't know how to do integrals, check, I don't know, I'll throw up some resources on the screen right now. Boom. Brush up on your integrals, but don't stress, you're going to practice a lot of integrals in this class. So this is the value, and we take this from 0 to a, okay? So now we have a squared over lowercase a squared. How I do this is first I plug in the upper limit, a cubed over 3, minus sign the lower limit, which is 0 over 3, which is literally just 0, which can just not be written. So now we have this. Now, what can we do here? Well, I see that there's 2 a's here and 3 a's here, so that cancels, leaves an a at the top. And that gives us a squared times lowercase a over 3. Nice. So that is the actual area. And that is not the same as this. There's a little bit of a difference. You guys see the difference? So keep that in mind. You got to do the integral. You can't just geometrically find the area. That is one mistake I've made. I've actually made that mistake many times in the past. Hopefully you guys don't make that mistake because you've seen what I've done here. Now let's do the second integral. The second integral is this one here from a to b. And what did we find the actual value of the integrals? You know what? I calculated all of this stuff, but I'm literally just going to take this because this is how it's given to us in the problem. We're going to integrate that. So we have capital A, b minus x, all of that divided by b minus a. Let's see if I remember that. And this is part 2, right? Because we did part 1 over here. So we have the integral from a to b, absolute value. Here we have, I think it's a, lowercase b minus x. And then here, I forgot what it was. Let's check again. B minus x, b minus a. Let's put brackets there for funsies. Absolute value squared. This is dx. So let's simplify this. Integral stays the same. Now we have a squared. Here we have b minus x squared, b minus a squared dx. Absolute value brackets are gone. This is a constant. This is a constant. Whoops, I should not have done this here. My mistake. That whole thing is squared. So both of those things are constants. It means we can pull them out of the integral. B minus a squared. The integral bounds stay the same from a to b. Now let's expand this bad boy. Or we could do u substitution. You guys want to do u substitution or should we expand it? Let's expand it because I don't want to do u substitution. Okay. So b minus x times b minus x. First, the b's get multiplied. That gives us b squared. Then we have b times minus x, which is minus bx. Then we have minus x times b. So minus bx again. We can make those into 2. And then that gives us minus x plus x squared dx. Let's erase one of these guys. Move this here. This will be 2 times this. Sometimes my b looks like 6. Sorry about that. Now we gotta integrate each of these one at a time. So let's keep the constant here out front. Don't forget your constant. Squared ab. Actually, no, we can already integrate, so we don't need to have the integral sign here. Integral of b squared is b squared times x, because if you integrate, or if you take a derivative of that, you just get b squared. Integral of 2bx is minus bx squared, because there's a 2 in the denominator, and the 2 cancels with the 2 over there in the front. And then here we have plus x cubed over 3. All of this is taken from a to b. Oh man, simplifying this is going to be a headache. All right, let's keep it going. We have a squared, yeah, b minus a squared. Now let's do the upper bound. So this becomes b cubed because b squared times another b. This becomes my b cubed again. Let's go, some simplification here. Then we have plus b cubed over 3. Okay, I'm going to put big brackets around this because we have to subtract the lower limit there. You see what I'm saying? So now we have a, so we have b squared a minus ba squared plus a cubed over 3. Okay, what can we simplify here? So here we have b cubed minus b cubed. Then we have, I guess that's everything we can do, huh? Equals. So here we have a squared over b minus a squared. Now what we have is b cubed over 3, subtract b squared over a, subtract ba squared, plus, oh, my bad, subtract, this is minus minus, so this becomes a plus, this is minus, so it becomes a minus, a cubed over 3. You guys see, because we subtract everything here, we subtract this entire thing, so basically we're subtracting this, so this becomes a plus, plus, And we're subtracting this, so this becomes a minus minus. Boom, close that bad boy. Should we simplify this anymore? Honestly, I don't want to simplify it because it looks kind of poo-poo. So I'm just gonna put a big red box around it. Okay, now you can see this clearly is not this. So you're gonna get a big incorrect answer. Now what we can do though is add up both of these parts. If we add those up, they equate to 1. And we have a over here. Let me actually copy paste this. Copy that. Paste. Let's clean it up a little. Move this here. Copy paste this whole thing. If you're working on paper, you gotta basically just rewrite it. Clean this up. Boom. Now we're adding these two guys. Adding them, this equals 1. Now take a look at this. Everything inside this equation is either a capital A, a lowercase b, or just a simple number. So we can isolate for capital A, and on the other side we're going to have lowercase a's, lowercase b's, and just numbers. Is that okay with you guys? Now the question is, how do we isolate A? Well, we have a squared here and a squared here, and to my knowledge, these are the only two a's, which is fantastic. So we could take both of these guys, factor them out. Oh my god, this is looking messy, guys. I'm actually scared. Is this the right answer? How do we even check if this is the right answer? Alright guys, I am so sorry about that. My dogs were barking like crazy. Right now they're not. And the last place I stopped was when I was trying to simplify this whole mess, because basically we have a squared over here. So if we take this entire thing in brackets and we divide it on the other side, we get 1 divided by this whole thing. So that's what I was trying to do here. I was trying to do 1 over this whole thing and then simplify this whole thing. But as you can see on the side of my screen here, I plugged it into a simplify thing. Listen, this could be cheating, this could be not cheating. Honestly, bro, on a test, if you get something like this and you say a is the square root of 1 over this, honestly, I think you're going to be chilling. But it looks like the answer is 3 over b, and then we have a is the square root of that, so we get square root of 3 over b. And I know this is right because I have found the solutions. The solutions are right here. I check this just to see if my final answer is right. I don't follow this. If you want, you can follow this. Here's the freaking solution. But boom, we got a equals square root of 3 over b, which is what our answer is. Square root of 3 over b. So I'm going to close this simplified calculator. You can use that for your homework if you want. Honestly, on a test, don't stress about this. But it seems like what the problem was, if you guys are interested in this, is when I did this second integral, I actually decided to expand this. Maybe it would have been better to not expand this and not do this whole integral, because things would have been kept very clean here. If you look at this part over here, you can see there's a b cubed over 3 and then a minus a cubed over 3. And then we have these kind of interesting terms, minus b squared a plus b a squared. This, I think, is some kind of like, it can be reduced to some kind of cube thing, or I honestly don't know, but you could reduce this if you're a math whiz, and then it should cancel nicely with this. But in the expanded form, it looks very ugly like this. It's going to take a hot minute to simplify this. Honestly, I have no clue how to simplify. That's why I pulled out the simplified calculator. So we got the final answer. If you don't have the final answer, you're going to struggle. But let's say you're on a test and you're like, hey, I really don't know how to do this. Could you please just give me the value of a so I can proceed with my work? If the teacher is like, no, I'm not going to give you the value of a, then you can say a is equal to the square root of 1 over this whole thing here. And then for the next part, you can be like, I don't know what a is, but I'm just going to say it equals 1, or it equals 2, or it equals some random number, and then proceed with your calculations. You're going to lose some marks. This is life, guys. I don't know how to do integrals. This is a physics course, all right? If you want to do math, you got to check another YouTube channel. But we got the answer. So let's go back. Let's check what we've done so far and what we have to do in the future. We have found a. Let's go in red, actually, here. Let's use some red. Boom, we did a. Boom, we did b. So we can plot this. Where is the particle most likely to be found? When you do this and this and this problem, you're going to have the value of A. Let's actually copy this. So if you want to do B, here is psi as a function of x, here is x, here is this slope, here we reach a value of square root of, is it 3 over b? Yes. 3 over b. This here is x equals 0. This here is x equals a. And then we go down here and we hit x equals b. You can hit, this is the slope from part 2. And this here is the slope from part 1. If you want, you can write these slopes. And this picture here should give you 100% for part B. Now let's do part C. And let's bring back the picture. So, part C. Where is the particle most likely to be found at t equals 0? I think this is the answer. At x equals a. Why is that the case? Because over here, the probability distribution is the highest. So if you measure, sure, you might get the particle here, sure, you might get the particle here, but most of the time you're going to find it here because that's where the probability distribution is the highest. So it has the highest probability of being found there. Where's the particle most likely to be found? Now, like I said, and like I read in the book, this most likely is kind of confusing. What does it mean? I don't know, but we're going to say this and we're going to move on. We're going to see if the answer is correct or incorrect. I think the expectation value of x is going to be a bit easier. So we're going to do that, and then we're going to go back to D. Is that okay with you guys? So if you remember from the book, expectation value of anything, let's just do like q over here, is basically integral from negative infinity to infinity. We're going to do more integrals of q, and then I think here we do psi squared, or expectation value is written a little weird. Psi star psi, and then you put a q in here, and then you do a dx. But psi star psi is basically, if you take this and you take this, it's basically this. All right, so we're going to check the book very quick. Here we go. Section 1.5. For a particle in state psi, the expectation value of x is, and then we do this. Great. So what we're going to do is pull out the white color, expectation value of x. So we're looking for this. What is this? Basically, we can do, well, like I said, from 0 to a, this integral is 0. So we don't even need to do that. We can just do the integral from a to b, because that's where the wave function is non-zero. So we could just take the integral from here to here. The integral from here to here is the same as the integral from here to here, because over here the wave function is 0 and over here the wave function is 0. So I'm just going to simplify this, skipping a couple steps. We're going to plug in an x over here, and we have to do the wave function squared. Oh, so we have to split it up again. So we have to do from, my bad. It was not from a, it was from 0 to a. So here we have x. The wave function here was a over ax. But now we can actually replace this a with the value we found, which is square root of 3 over b. Is that the value we found? Square root of 3 over b. Then here we have a dx. Then we can add this to a b. We have an x here. Oh my god, we also have to do the wave function squared, so it's this whole thing squared. And this is getting complicated. Okay, now here we have another function, which is that complicated one, slightly more complicated. Where to go? Here it is. So take this, copy that bad boy, go down here, paste that bad boy, and then we can make it clean, erase that, erase this, erase a, replace a for square root of 3 over b. Okay, now here we have a dx. So if we solve this integral, or these two integrals, we're going to find the expectation value of x. Let's hope this is easier to simplify. Maybe I'm going to do my integrals a bit differently now, so I'm not cheating. We have equals 0a. What we have here is x cubed, because there's an x on the outside and x squared here. Then what we have is 3 over b, the square root gets removed, and then here we have a squared. Then here we have dx. Plus, I'm going to simplify all this later. Here we have this. So what can we simplify here? The x stays like that. Then we have 3 over b here. Here we have a b minus x squared. I'm not going to expand that this time. Maybe we're going to do u sub or something. I'm not sure. Then we have a b minus a, and then here we have squared. Then here we have a dx. So let's do these one at a time. Here is integral 1, and over here we're going to do integral 2. Let's do integral 1 in this color. Okay, what is this integral? We can pull some constants out. We can actually pull most things out. Here we have a 3. In the denominator, we have the ba squared. Nice. Then here we have integral from 0 to a. This is x cubed. This looks like a simple integral. We have 3 over ba squared. The integral here is x to the 4th power over 4. Then here we have the values. Boom. Now we can do an equal sign. In the denominator, we have ba squared. We have a 3 over here. Now here we have a to the 4th over 4 minus 0 over 4. So we just have this. Let's simplify this a little bit more. So we have 2 a's here. Cancels this, gives us a 2. So it looks like this is as simple as we can get it. So we have a 3 over 4. I'm just going to pull out the numbers. Then we have an a squared over b. And this is our answer for integral 1. Now let's do integral 2 in this color. So we can pull out a few things. We can pull out b minus a. This is squared. Then we have a b in the denominator, and we have a 3 on the top. Then we have a and b over here. What is inside the integral is x b minus x squared dx. How do you solve this integral without getting yourself really in a pickle? I don't think you could do u sub, because if I say this is equal to u is equal to b minus x, then du is just going to be minus dx. And you know what? We're going to do a u sub, guys. We're going to do a u sub. So let's keep going with this pink color here. b minus a squared. Here we have, oh, and we have to change the bounds. Brother. Okay. The lower bound is u, but you plug in a. So this is going to be b minus a, right? Because I'm using this equation to find the new u1. Then we have here b minus b. I don't like this. I don't like this one bit, because b minus b gives you 0. And you need to have the lower bound be a smaller number. So we have to flip this integral, and the way we flip it is we add a minus sign over here. Okay, you know what? We're going to keep going with this. 0, here we had b minus a, and b minus a is a bigger number than 0 because b is bigger than a. All right, now what we could do is replace this x over here by using this equation. And how we do that is we move x on this side, we move u on that side. So x is equal to b minus u. B minus u. Inside the u sub, bro, this gives us literally the same thing. Okay. Dude, this u sub is not working, because inside the brackets here we have u squared, and we have to FOIL anyway. Oh my goodness. And we have a negative dx, which is going to give us a du, and this negative sign cancels this negative sign. Okay, so I guess that's not bad. We're too far in, guys. We're too far in. We're going to do u sub anyway. At this stage, I have literally no clue what to do except for distribution. So we're going to do a distribution. b minus a squared over 3. Here we have 0. Here we have b minus a. So we have b u squared, and then we have minus u cubed. This doesn't look too bad. This does not look too bad. We'll see if I made any mistakes in my u sub. If we made a singular mistake, we're screwed. Add an extra page right here. We're going to keep writing, so 3 in the numerator. Can't pull any constants out yet. B minus a squared. 0, b minus a. I think the u sub was actually better because now we have one of the bounds being 0. So it's going to be a bit more simple, I think. Actually, we don't even need this integral because we're ready to integrate at this stage. Okay, big bracket. And now we have b. This becomes u cubed over 3 minus u to the 4th power over 4. We close this. The upper bound is b minus a. The lower bound is 0. We are ready to integrate for realsies b minus a squared 3. What is the first thing? B minus a. Oh my god, we got cubes and stuff. Oh my goodness. Is this really the right way to do the problem? I don't know, but we're in the same boat here. So this becomes cubed. Now we have a 3 over here. Oh my god, and we have a 4th power too. A 4th power 4 minus the other stuff gives you 0 because you plug in 0 into the u. How do we even simplify this? Wait a second. We can cancel quite a few of these. Check this out. There's 2 of these b minus a's here. That cancels with all of these except one of them, and it cancels with all of these except this one. That's beautiful. But basically factor out a b minus a term, and we cancel it with those. Okay, so can we do anything else? Let's just simplify here, use white. So here we have 3 over b. And now inside what we have is b minus a 3 minus b minus a squared over 4. Holy guacamole, guys. All right, skaboom. Let's get our first value here. Skaboom. Copy this. And what we said was if we add those up, then we get the value of x, the expectation value of x. So we did this integral, we did this integral. We add them up, and we get expectation value of x. Expectation value of x is equal to the first thing here plus 3 over b. I'm basically writing this whole thing here. b minus a. I'm sure this is going to simplify to something super goofy like square root of a or something like this. Minus b minus a squared over 4. So this is the answer. This is the expectation value of x. Okay, so we get an interesting answer. I use the simplification symbolab thing. b plus 2a over 4. I guess we should also check the answers. Okay. Here is the answer for the expectation value of x. And we get the right answer. All this simplification, guys, don't stress about it. Just say at the end of your class, like if you're actually doing this on a test, you can just circle this and say, I'm not good at math. And your professor will mark this correct because this is the correct answer. It doesn't matter if you simplify or not, or you guys are not like AI supercomputers over here. All you need to do to get an A in this class is know the theory, and the theory is you plug stuff in, you do the integral, no need to simplify. But if you're on a homework, it's nice to simplify. So we see that this is the right answer. Nice. Now we can go back. So what we have done is we normalized psi. So we found A. We did a sketch of psi. Where's the most likely place to find it? We did that over here. We're going to check if that's the right answer. Actually, let's check if that's the right answer right now. Okay, here we can see from both graphs that x equals a is where the particle is most likely to be. and the particle cannot be here and here. So we got that problem right as well. Nice. Then we just found the expectation value. So all we have to do is this. Paste the question right here. We solve this, we solve this, we solve this, we solve this. All we have left is D. Now let's do D. Where is the probability of finding the particle to the left of A? So we have psi of x, which looks like this. Over here is A. So what is the probability of finding the particle here? Check your result in the limiting case. B equals A and B equals 2A. What does this mean? B equals A, B equals 2A? I'm not sure, but I do know from the book that the integral from x1 to x2 of the probability distribution squared, this gives you the probability of finding the particle between x1 and x2. So what's the probability of finding the particle on the left side of A? Basically, we have to solve this integral from 0 to A. From 0 to A, we have A over AX dx as the wave function. And what we have to do is square that, and what we can also do is replace this by 3 over B, square root of that. Is that the answer we got? Square root 3 over B. So this looks like a fun and easy integral to do. What we can do is pull out the integral, or pull out some of the constants. So we have 3 over AB. A is squared, and the square root from the 3 over B gets removed. Then we have 0 to A. We have x squared dx. Oh my goodness. And by the way, we should just get a number here. Like we should get straight up a number because it's probability. Probability is a number. I would be uncomfortable getting a probability in terms of A and B, but maybe that's actually going to happen. So we will see. Let's do the integral here. A squared B in the denominator. We have a 3 here. We can integrate right away. So this is x cubed over 3. Here we have a 0. Here we have an A. So we have 3 in the numerator. A squared B. What we have here is A cubed, interesting, over 3 minus 0. So this is our answer. What we can do here is cancel these two with this, cancel this 3 with this. A over B, interesting. So probability is equal to A over B. So that is the answer. Now let's go back and check, what does this mean? Check your result in the limiting case where B is equal to A and B is equal to 2A. Okay, the limiting case. So actually, let me write this one. Case 1, B is equal to A. So the probability, if B is equal to A, let's write this in white. Probability if B is equal to A, then we have A over A, which equals 1. So if B is equal to A, the wave function looks like this. It goes up here, and then it goes straight down, and then it goes like this. So the probability of finding the particle to the left of A, so the probability of finding the particle here is 100%, because we've done the limiting case where B equals A. So instead of B being here, we move B right here, and the wave function changes and looks like this. So this actually makes sense. Now let's check case 2. B is equal to 2A. Is that case 2? B is equal to 2A. So then the probability, which we found before, was A over B. But now B is equal to 2A. So these A's cancel, and we have 1 over 2. So what this is saying is, if the wave function looks like this, it goes up. Here we have A, and then it goes down. Here we used to have b, but now this is 2a. So what? Hello guys, here I ran out of audio, so I'm re-recording. Basically, I'm just coloring in half of this thing to show you that the function is symmetric. So the left side of a is half, which is 1/2 over here. We're going to check the answers right now. Remember, don't check the answers unless it's for the final check. Don't follow these solutions. So here I have a over b. That is what we got. For the limiting case b equals a, p equals 1. We got that. And for the other limiting case, b equals 2a, probability equals 1/2. So we got the right answer. Thank you guys for watching. I know the video was very long. You guys got this. Do the problems on your own. Drop a comment if you have any problems that you want me to do or anything like this. I'll see you guys in the next video. And remember, you can find the solutions online, but do not use them. Just use them to check your final answer. Try to do the work by yourself. Otherwise, you may make a mistake like this on an exam or a quiz or something like this. So try it out by yourself. Let me know what you're struggling with specifically, and let me know what you want to see in future videos. Thank you guys for watching. Peace out.